let's make a start. Hit 5:30. Cool. So for this review class, depending on attendance, we might split it across a couple of different topics. I did see that you requested to have a look at the square root type graphs and sort of revise those from the ground up, so we can definitely do that. There was also some parts in class 2 that we didn't quite finish up, that being on the last parts of the definite integral. So we had a look at like these properties of definite integral, but we didn't quite look at the stuff on unsigned area, bound area, total area, that sort of thing. So we'll start off with this. We'll do maybe half of the class on that, or as much as is needed for that, and then we'll move on to the last topic there. Cool. So square root graphs. It's actually surprisingly one of the more complicated kinds of graphs because it has a few separate nuances to it. It's one of the only graphs that can have no intercepts, for starters, and it's one of the only times where algebraically trying to solve for certain things might give you a false positive, which is, I can't think of any other circumstance or any other graph type that does that. So let's explore it a little bit. So first up, without any transformations, the basic square root graph looks like this. It actually comes from essentially half of a inverted hyperbola, inverted parabola rather. Normally we have the parabola of x squared going up here, but if you imagine the graph of like y squared being equal to x, it kind of goes on its side. Then when you go ahead and to square root that, depending on whether you have the positive or the negative root, you're having either the top or the bottom of that particular graph, which is why when we do our square root x, positive square root x, we're only getting that top half of that. So similar to how a parabola works, the square root also has a vertex. It's a little bit inaccurate to call this a turning point, like we would for the quadratic, for the parabola. So the more general term there will be the vertex or the starting point of the graph. And obviously depending on where this is, we may or may not have any particular intercepts. Joined late. Yeah, so going to quickly, just to recap the agenda, we're going to spend some time revising the square root graphs and then move on to finishing up the last little bit that I didn't quite mention last time we were doing definite integrals, that being for the bound area and unsigned total, all the area related stuff that's in the latter half of the definite integral document. Okay, where was I? Cool. So yes, square root. Just like any other function, it has dilation factors and they work the same way as they do for all the other functions. If you have a multiplier on the front of your square root, it is going to dilate it or stretch it in the y direction. So when you have 3 root x, it's obviously now going to climb up higher. As far as you drawing this by hand, you can pretty much ignore any of the dilation factors. They're not going to actually impact any decision making. All they'll really do is change what your algebra looks like, and that's pretty much it. Because when you set your own axes, the difference between that graph and that graph, if you're only drawing one of them, like it's just the same overall shape. Similar thing here with the dilation factor in the x direction. So again, as that denominator gets bigger, it goes further in the x direction, and if it gets closer to 0, well, you get the opposite effect. These are more so things to do to understand how the graph behaves, but less so when it comes to actually sketching it yourself. Just like we explored a little bit earlier, when you have the negative square root, you're essentially flipping it downwards, and when you have both of them on the same axes, you go right back to having that y squared equals x graph. So if you just have the negative, you're going to have the bottom half. If you have the positive, you have the top half. You're reflecting it in the x-axis, or about the x-axis, which is the exact same notation for all the other functions. Anytime you have a negative sign on the very front of the function, that is a flip vertically. One of the things that might appear strange about the square root is that you can actually have square root negative x. That will in fact reflect it across the y-axis or horizontally. The first typical objection I see to this is, hang on, I thought we weren't allowed to have negatives inside of square roots. the real answer to that is you can't have negative numbers inside of square roots, but you can have negative variables. And the reason why is because this variable, so long as it exists in the domain, could be realistically any number, both positive or negative. So if you were to chuck in a negative value for that x, then you suddenly have negative negative, which shoots back up to being positive, which is the other algebraic reason why instead of going up and to the right, we're now going up and to the left. We're only defined for the negative x values rather than the positive ones. That's why the graph is only ever in a certain quadrant. It's because of the fact that you can't have negative numbers inside of your square root. That's one of the first weird things about this. So I guess I'll pause there real quick. Is there any questions or clarifications for that? And again, you can chuck it in the chat as well, and I'll go back on it. Easy. Cool. As for translations, again, they're going to work the same as any other graph. X minus h, so whenever you have minus in your directly attached to the x, you now have a horizontal translation to the right. Plus is going to be left. Exact same rules as quadratics and all your other functions. You can sort of think of that as setting the location, or rather the x location of your vertex. If you have x minus 2, you're shifting it right by 2. If you have x plus 1, you're shifting the vertex left by 1. Vertical translation, it always looks like a plus on the very end of your function. Plus goes up, minus goes down. Same. And so basically your two translation terms are going to set the location of your vertex, just like it would for the quadratic, right? You'd have your horizontal and vertical component, which give you the location of the turning point. In this case, it gives you the location of the vertex. Here's a big old procedure for that. So if you want to have a nice little copy of that, I can chuck that in the chat. It's also available, of course, in the classroom section under functions and relations, miscellaneous graphs. You can find all these documents here for it as well, with all the key examples. Cool. Let's have a look at an example. It's going to be a fairly complicated example with all of the key features involved. So you've got all of the different factors in there. But that's simply to show you that if this procedure works for the more complicated one, it'll definitely work for the ones that are a lot simpler. Like if you have a look at like the Unit 1 and 2 book, the worst they get is they'll do a bit of weird rearranging. But this one, you know, you'll have a reflection and two translations. This one's dilate, reflect, translate. So they get kind of like there, but I've just sort of gone out of my way to put something in more or less every spot. Cool, okay. So step one in pretty much any of my procedures for sketching graphs is I'll always default to trying to rearrange whatever graph I have to its general form. We kind of skipped on this quite earlier on when we had a look at this. This is what it looks like when the square root has all of its key features essentially rearranged in an easy to digest way. You can see your horizontal translation, you can see your vertical translation, you can see your two dilation factors, and if there's any negatives, well, those will go either on the A or like outside these brackets. But if we look at the example that we have, it doesn't quite match that perfectly. The main issue is going to be this dilation factor on the X specifically. So the only thing that's going to matter the most here is taking that out as a common factor. More so just to clearly see what the true translation factor is. Because just looking at this, you might be tempted to think that you're shifting right by 3, when in reality this dilation factor actually plays a role in that. So taking that out reveals the true horizontal translation is actually going to be 1 to the right, which is what we're going to see in these two sections here. Another way you can think of this, square roots are only defined from the inside of the root being from 0 to infinity. You can never have any negatives. So when we're thinking of our vertex, the very start point, the vertex, is going to start when the inside of the root is 0. So in other words, where does 3x minus 3 equal 0? Well, when x equals 1. That's what this is revealing. So it's just another way of revealing where it's going to start, rather than you having to do a bit of algebra and solving for a thing. Those are the two main ways you can handle that, and this is true of all functions, not just square roots. Anytime you have a dilation factor on the x, either do some math to solve where your translation term should be, or just do a bit of factorizing to reveal it properly. But okay, so once we have that in its form, we can clearly identify all the key things. The starting point, the vertex, is going to be determined by the horizontal and vertical translation. As we discussed, shift right by 1, shift up by 1. Bang, bang. Next up, axes intercepts. So you can go ahead and try to solve them all ahead of time and then just let the math be what it's going to be and then dot it out accordingly. But it can be kind of nice to try and get an idea of what it's going to look like ahead of time so you can save a bit of time rather than solving things that may or may not exist. How do we do that? Well, up until this point, we know where the starting point is, so we can definitely dot that one out there to start with. Then from there, all I'm doing is looking for the existence of any reflection terms. We got 1 out here. There could also be 1 on the inside of the root as well. This reflection term tells me that it's going to be reflected vertically. It's going to go, rather than up and right, it's now going to go down and right, which is why you get this sort of shape going on. So if I know I'm starting at 1, 1, and my graph is now going to go down and right, because it normally goes up and right, we got that reflection, then just without even labeling any of this, I know I've got an x-intercept, but I've got no y-intercept. So that can help you save some time. Any questions about the logic behind that? Looking at the reflection terms, and then based off of where you put your vertex, can determine how many intercepts you have. Cool. Once you identify that you have those intercepts, you can go ahead and now find them. In this case, we know there's not going to be a y-intercept, so when you do your math, it's not going to quite work out too well. For instance, you shove in your x equals 0 to find your y-intercept, and suddenly you get a square root of a negative number. Bad, not going to happen. So we know already, stop continuing from there. X-intercept does work, so that's going to be y equals 0. Rearrange, rearrange, rearrange. This is all just algebra, right? Subtract 1, divide by negative 2, gets you here. Square both sides, gets you there, and so on and so forth. This is just linear at that point. If you have a domain restriction, you'll just simply find the endpoints by subbing those in to your function. Typically, you don't really have a domain restriction on these sort of things, or if you do, it won't be on the vertex. It'll be something like a little bit afterwards. So typically, you're only ever going to find one of those endpoints additionally. But yeah, so we found our x-intercept was going to be that, found our vertex, and just knowing those two things is enough to already draw the curve. Any questions about that one so far? Cool. Here's the last thing that's worth discussing about the square root, and that is that sometimes the math can actually mislead you. So, square root of x plus 1. We should already know more or less by identifying where our vertex is and the fact that it's a positive root, that it should go up and right. Right, it's a positive root, it'll go up and right. It's got a vertex at 0, 1 because there's no horizontal translation, but there's a vertical translation of 1. We would expect to have this green graph here, right? So knowing that, we should already say, well, okay, I found my y-intercept. It is just the vertex. There's no x-intercept. Oddly enough, if you try to find one, you will actually find one. So square root of x plus 1, if you try to find that x-intercept, y equals 0, subtract 1 from both sides, square both sides, what you find is x equals 1. That's pretty weird, because we're supposed to have this graph. The reason why you find that is got to do with the fact that we're only really taking one part of the square root. We're only taking the positive part because we are taking positive root x. What it's finding is the x-intercept that would have existed had we looked at the negative component. So this is one of the times where doing the algebra as you normally do it sometimes just gives you a false positive. which is very important to understand, because this is why we try to look ahead of time and figure out, well, okay, what does this graph actually look like? Mainly going to be around where's my vertex and what are my reflection terms. Those are the main things you're looking for to get this overall shape. And from there, you can use that to do a bit of damage control if you do somehow accidentally go down this route of finding sort of false intercepts. But okay, let's take a stab at one of these questions, unless there's any further things I should clarify. We'll have a look at something like 3D seems about right. Yeah, we'll just sketch this one end to end, 3D. So that's going to be y equals square root 2 bracket 3 take x. And that's that. Cool. Yeah, we're just going to sketch it end to end. All of the additional little things that it mentions, we can also then include in our answer, because sketching the full thing just kind of tells you things like domain and range just by looking at it. Right, like when you look at your final answer, you just look at all the x values it spans across, you look at all the y values that it spans across. All right, so on the screen share, I'll have the summary of the overall procedure we're going to follow. You've also got a screen grab of that if you prefer to have a look at that. With that in mind, does anyone want to take a stab at how we might start this one out? I don't think I'm thinking straight. Square root 4 plus minus 2, so wouldn't the square root function not be a function? So square root of 4, it's because of, yeah, it's a really weird part of math. Square root of 4, why is it? Yeah, so square root of 4 is going to be plus minus 2. What's wrong with that? I don't know if I have a super nice answer for you, other than to maybe look at every instance where we do have plus minuses. It's actually explicitly told to us in the like in the equation itself. So for instance, if I pull up like the quadratic formula, if I pull up the quadratic formula here, if the square root already naturally gave us both plus and minus answers, then this would be a redundant symbol. We wouldn't need to include a plus minus here. So square root naturally only has that solution. Putting the plus minus in there explicitly tells us that we have both the positive and the negative, or that we're including both the positive and the negative options. So if you leave that out, you're only including the positive. Or if you have the negative in the front, you're obviously only including the negative possibility. That's probably the best that I can give as an answer for that for now. Definitely something you can Wikipedia up and find more sophisticated answers for that, but I hope that's going to do for now. Okay. Sweet. Cool. Okay. So in regards to sketching this one, any thoughts on how we're going to start this out?
We try and find the vertex thing.
Yep, finding the vertex, absolutely. What are we going to do to find that?
We look at the translation.
Yep. This is where things are going to get maybe a little bit tricky. What is that translation?
So the 3 minus x, that's in reverse order. We can take a negative out.
Yes.
Yeah, we can work from there.
That's good. So that's sort of like the step one in the little procedure that I've got on the screen grab, which is making sure that you're taking, this is technically a coefficient on the x, -1. So taking any coefficients off of the x reveals what that true translation term is now going to look like, which in this case is obviously now...
Yep. Now, there's a translation of 3 units to the right.
Absolutely. Yeah.
So
So
0,
our
3.
3, 0 for this one, it's
Oh
horizontal.
yeah, 3, 0.
So yeah. But yeah, so that's going to give us 3, 0. We got this implied +0 for our vertical translation there. Cool. Okay, that's step 1 and 2 done. Next up, finding the axes intercepts. We can just try to smash them all out and then let the algebra be what it is. But let's practice a little bit about trying to identify what our shape might look like here. So dotting out the only key feature we know so far, the 3, 0 bit, we know our vertex is here. All we got to do now is figure out what direction is it headed. Because normally, without any other things, it would go up and right. Based on what we're seeing in our graph, what's actually going to be the case here?
It's going to be reflected on the y-axis.
That's it. Yeah, that negative sign there implies a reflection in the y-axis. So rather than going in that direction, we know we're going in this direction, which tells us we should now actually try to find that y-intercept. Y-intercept is always x equals 0. Y equals square root -2 bracket 0 take 3. So -3, -2 makes 6. Y equals √6, or what's that going to be? So 3, 2. That's just it, actually, isn't it? √6. √6. That's pretty much it. So we got our graph sketched. If we did have like a vertical translation, for instance, then if it was up, we might not have an x-intercept. If it was down, it would be in a different location. That gets us our graph. As for now, going like, let's say, the domain and range part of this, domain and range we can now just observe directly off of the graph. So what is our domain going to be?
The domain is going to be -infinity to 3.
That's it. Yeah. One nuance about the root, 0 is considered inclusive. There are other graphs that have a similar thing where it's non-inclusive. The one coming to mind is going to be the log, right? Log 0 doesn't actually get included, but for square roots it is inclusive. This is a bit more like what we're already used to, because the quadratic does the exact same thing. It's definitely included in the quadratic. Okay, that's domain. And then range, again, looking at all the possible y values, that's going to be what?
Zero to infinity.
0 to infinity, yeah. Clearly starts at 0, and because it's an ever-increasing graph, it'll shoot off to infinity. 0, infinity. Making sure, of course, we put those rounded brackets on the infinity, but that's what you do for all graphs anyway. Cool. That's about it for the square roots, I guess. Do we need to practice any more? Like, I'll pull up the chapter section there. If there's any in there that look like they should be covered, let me know. 3D more or less covers a decent portion of it. Some of them have, reflections in different places, maybe a little bit of rearranging to be done, but otherwise it's all more or less the same sort of thing. Should we do another example? Yeah, we should probably actually, yeah. That'll split the class 50-50 actually. I'll spend the last 5 minutes doing another example. Cool. What's another one? Yeah, I do actually like doing... I'll just make my own one up actually. Y equals negative square root 3x take 3. plus 1. Cool. All right, same story. How are we going to start this one out? Okay. One of the main things we want to do here is just make sure we can be clear on what all the translation terms are, or transformation terms are. Dilation factors on the x are something to be removed or factorized out. So it's really good practice to go ahead and start with that, taking that comma factor of 3 out the front, which now reveals the true horizontal translation of of 3 to the right. Alternatively, if you don't like doing this whole factorizing thing, one of the things you can do is use your intuition on functions themselves. So if we know the square root is only defined from inside of the root being from 0 to infinity, then we can literally just try to solve that exactly that. So essentially, 3x take 3 equals 0 is the breakpoint of that thing. So we have 3x equals 3, x equals 1. Yeah, which means I did my factorization stupidly. That's what I'm just looking at now. Because, yeah, that should have actually been there. So you got two separate ways of doing it there, depending on if you prefer the algebra approach or if you prefer the just general purpose factorizing out any coefficients there. So that's going to get us our horizontal translation of 1. Vertical translation is also here of +1 as well. So our vertex 1, 1. Once again, we'll get that all sorted here. 1, 1. What we're going to do now is look at our reflection terms and identify, do we need to bother finding any of the intercepts? Because if it goes up here, we're already done. Nothing else to be done. But if it goes like, I don't know, like this, then we've got two things to find. So, based on these reflections, what direction do we expect the graph to go in? Got at least one reflection involved. Bottom right, yeah, that's it. It's going to shift, so that's a reflection in the vertically reflected. So yeah, it's going to shoot down to the bottom right now. Absolutely. Which means the only thing we have to find is going to be that x-intercept. Y-intercept, we're not going to bother finding. If we did need to find it, by the way, x equals 0, suddenly you got -3 in the root. So nice and easy way to stop yourself from going too far. Just like before, x-intercepts, let y equal 0. 0 equals negative square root 3 bracket x take 1 plus 1. And the algebra here should be fairly okay. Subtract 1 from both sides, divide by -1. Root 3 bracket x take 1. Square both sides. 3 bracket x take 1. 1 on 3, x take 1. 4 on 3 is our x. Quick sanity check, 4 on 3 is indeed bigger than 1, so that number makes enough sense for the root. Obviously, don't do it as fast as what I just did there if you're definitely wanting to make sure it's in a you're going to get the mark in the actual sack. But yeah, and that'll be it. As far as domain and range, again, we're just going to look at it. How far does it stretch horizontally? Well, starts at 1, goes all the way to the right. How far does it go vertically? Again, starts at 1 and goes all the way to the bottom this time. Oh, anything further to clarify regarding roots? Because if not, we could move on to the integral related stuff probably at this point. let's do that then. Close that bit off. I'm noticing we have a few new faces from who probably haven't been here for class 2, so I'll quickly just recap or give an overview. What are we actually doing with the definite integral? I think at this point, most of you have been here for the antiderivative. What we're essentially doing is taking the antiderivative a step further and putting these boundaries on our definite integral. Those are known as the terminals of the integral. One of the key applications of integration is, or anti-differentiation, is to find area under a curve. And those boundaries, the A and the B, are essentially limiting your domain for which you're evaluating area. There's a whole little thing you can look into as to why it does that, if you're interested in the reason why. For now, we're just going to take it for granted as for what that actually does. How do we actually evaluate this so-called definite integral? Well, first things first is going to be the actual antiderivative itself. So find our capital F of x by doing our antiderivative. This is done via just a basic lookup table of your antidiffs. So this will be on your formula sheet. I'll pull up my summary of that real quick. Where's that? Integration. So basically you're looking at the left-hand side of this and then just replacing whatever it is with the right-hand side. So in this case, it's a quadratic, right? It's all power, functions, and constants. So we're looking at the power function and constant version. It's just plug and play, right? Whatever the power is n, and you're just placing it with whatever's on the right-hand side. We'll practice more of the actual doing the antidiff when we start doing some questions. But for now, to sort of take it for granted, again, we're just raising that power and then dividing by that raised power, getting the antidiff down. From there, when you actually do your definite integral part of it, whatever you're doing top, take, bottom. So whatever the top is, take whatever the bottom is. And you're subbing that into the new function that you've just created. This is now just pure algebra, right? So you look at the top there, it's 4. Look at the bottom, it's 2. That means we're doing capital F of 4 minus capital F of 2. And this is something everyone can do, so long as you have strong arithmetic. As we can see, this does get a bit lengthy. So one of the issues that you'll start running into, especially when you start doing more complicated things with more functions, is this will take more than a single line on your page. So rather than do it all in a single line like I've written here, you might consider saying, okay, I know I need to do f of 4 minus f of 2. Maybe on one line I'll just do f of 4, simplify that all the way down. And then on the other line I'll do f of 2, simplify that all the way down. And then finally combine them at the end. That's one thing you can do. In fact, it's effectively basically the same thing as what I've just done here. The only reason why you would consider probably doing it all in one line is, well, 1, if it fits, then go ahead. But 2, because they're the same function, you often have opportunities of factorization in your arithmetic. So if you look at like some of the similarities between these, there's potentially coefficients that could be taken out that can really help speed things along. But okay, so we simplify things all the way down. One thing we'll note is that plus c's will always disappear because you got a plus c on this side, a plus c on that side, both separated by a subtraction. So what you'll find oftentimes in any work solutions that you look at, they just don't include the plus c in either of these. They might include it in the capital F, just because technically that is part of the antiderivative, but when you're actually evaluating the definite integral, it'll never play a role. So it's often left out, and that saves you at least 4 characters per line. That's a basic overview of what the definite integral is and how we evaluate it. There's a few properties in which you can use to manipulate definite integrals and sort of split them up and evaluate them in separate sections. I don't think we'll be able to do that just today. So what we'll do instead will be having a look at the area related stuff for it. So how do we now use this to find area? literally all we're doing is doing exactly what we just suggested, definite integral. So if you get a question like, find the signed area of this quadratic over this interval, that's keyword for just saying, find the definite integral over that interval. So first you would antidiff that function, just take for granted that's what you get for antidiffing. Then you're looking at the upper and lower bound of your terminals and doing it in that order specifically, the upper and the lower arithmetic, and the answer you get is the area under that quadratic over that domain. So you are finding this red bit and this green bit, what that area ends up becoming. Now, a bit about the terminology for this. This is referred to as signed area. The reason it's called signed area is because it has a sign, either positive or negative. And positive or negative area is handled or interpreted differently. Area that is below the x-axis is considered negative. So that's going to be that red spot on the graph. So if you were to simply just do the definite integral from 1 to 2, you would actually get a negative number from that. You get negative area. Anything above the x-axis is considered positive. So again, if you were to do the definite integral from 2 to 4, you get a positive result. So when we have done our definite integral from 1 to 4, what we have actually done is find this area and subtract this area from it. So this is a big positive, this is a small negative. When you do that subtraction between the two, you get 9. In fact, you can see, actually no, sorry, you'll only be able to see the terms if you split up the terminals, which is what we'll look at next. For now, is it fair enough differences between positive and negative area? Does any of that need to be clarified further? Sweet. This is something that's pretty much never, unless it's in the textbook, they'll only really ever use signed area in the textbook. Pretty much every time else they're referring to area, they are referring to it in the unsigned, total, or bound area terminology. That's the kind of terminology they'll use. In all of those cases, it's your job to interpret all area as positive. Unsigned, right? There's no sign, positive or negative, associated with it. You treat it all as positive. That poses a problem because just doing definite integral, by its very nature, treats things as signed. So we need to figure out a way to get around that. And there's a couple of things you can do to get around it. Both of them are going to stem from the fact that you're going to split this domain up. You're going to sketch your graph, what it looks like, and make sure that you're splitting it across the positive and negative sections. So in other words, we knew it was negative from 1 to 2, just by sketching our graph. We knew it was positive from 2 to 4. So rather than doing our definite integral from 1 to 4, we now have 2 separate sections that we're going to evaluate individually and then do some fixing up at the end. How do we do that? The simplest way to do it is to simply just evaluate this one and just slap a negative sign on it again. It's already going to come out to be some negative number. Literally just put that to be positive. That's all you need to do. And that's what this one here is suggesting, right? Instead of just doing the integral from a to b, or in this case, 1 to 2, we just now put a negative sign on it because we know we need to flip it back to being positive. The other thing you can do is flip the terminals themselves. So rather than go from a to b, we're now going from b to a. What that does mathematically is flip the order that you do this subtraction in. So instead of doing like 4 take 1 here, you would now do 1 take 4, which means that if this was overall dominant positive, now it's going to be overall dominant negative over here. It flips the order of the subtraction. You flip from positive to negative. This is actually detailed in this little summary here, which is to say that putting a negative sign on your integral is the same thing as flipping the terminals themselves. And as a whole, pretty much you'll be using any number of these 1 to 4 up here. 5 and 6 are niche, but they have appeared in exams before. And for those who weren't in the class 2 around it the Tuesday, this actually doesn't appear in your textbook either, and you needed it for the exam. So definitely make sure you have these in your bound reference, because if it comes up, you'll definitely want to have it. It was only a multi, by the way, like a 1 marker. So yeah, Tyan.
I was wondering, like, how helpful is like the study design, like as a checklist for what you need to know? Like, is it actually helpful, or
It's honestly more helpful for the textbook writers than anything else, because they take that and put the content in for the textbook stuff, and then the schools teach out of the textbook, basically. That's who it's really meant for, people who design courses around these things. You looking at the study design isn't going to help too much, I don't think. Like, yeah, sure, you can look at it yourself and know for certain, hey, these are the things that are expected, but they're very vague and open-ended. So it can be hard looking at that and be like, oh, okay, cool, so we're doing integrals, yes. How much of integrals do I need to know? And that's the answer, or that's the question that I find that doesn't get answered particularly well in the study design. That, or I'm just bad at interpreting things. One of the two.
okay? I was just wondering, like, if it was specific enough to use as like a checklist, like you can use it as a checklist for the knowledge. Because I know for like other subjects, like it's really good, but I don't know about methods.
Um, I mean, it can't hurt to have a look at it, but probably the best checklist is going to be making sure you can smash out all of the questions in the textbook that you provided, whether it's Jacaranda or Cambridge. Doing the review chapters, especially focusing on the extended response sections of each of those bits as well, because that's where all the bulk of the marks are going to be. The actual doingness of methods is quite straightforward. In fact, it's straightforward enough to where you can literally have step-by-step guides on how to do all the key questions. It's the fact they put worded scenarios around it and make it ambiguous, which is where you now have to use a bit more of your problem-solving skills to get there. Because, frankly, the tech-free exam, I did a work solution for it not long ago, and I'd say a solid 60 to 70% of it was pretty much just straight out of the textbook, basically. It might as well have been. So this is stuff that you can do that's quite repeatable over and over again, and just by being really strong in the textbook stuff here, you'll go quite well in tech-free. If you want to go quite well in tech-active, focusing on the extended response sections in this book would be a good start. The next spot would obviously then be the practice hacks that we have here, because those pull from a whole bunch of different places of extended responsey sections. Cool. Okay. So what I was mentioning here, right? Splitting up our terminals into both positive and negative sections, and essentially evaluating those individually each. So we know the negative section is from 1 to 2. One of the ways you can handle that, simply just put a negative sign on it ahead of time. So that's, again, using the same function, 1 to 2, but this time putting a negative sign there. Or, alternatively, just swap the order of it. Now do 2 to 1 instead of 1 to 2. Both of these will now make sure that both of those end up being positive. So when you add them together, you get a net positive result again. If you do the negative sign approach, you're essentially doing this arithmetic here. If you do the terminal swapping approach, the only thing that's different is this bit here, and there's no negative. So you can see how the math comes out to be quite similar, right? So you're still going to have a 5/3 in there. You're still going to have a 32/3 for this one. But this one's going to have a double negative, and this one's just going to already have been sorted out from the get-go. This comes out to be a bigger number. So, right, 12.33 versus the 9 that we had earlier. That's because the 9 was the addition of a positive and a negative number, whereas the 12.33 made this a positive and then added that on. So that's the bit of the lesson that I didn't quite get to when we ran class 2 last time. Is there anything about that that needs more clarification? If not, we can give it a shot. Where is it going to be? Area under curve, 11F. Yeah, keywords like exact area, bound area, those things are going to be what we just discussed there, which was making sure we're flipping any negatives to positives. If it just says like evaluate the definite integral or do the signed area, that's when you just do the definite integral with nothing else. Now, it does go out of its way to define signed area, but oddly enough, it doesn't actually end up using that terminology in any of the questions itself. It'll pretty much just do the definite integral, and that's it. So because the exact area or bound area stuff is the more involved one, even if it's actually starting us there anyway. So let's give that a shot. Just basically starting off at 1A, noting that it's exact, which means we need to be considering where do we have positive and where do we have negative. I'll start writing that one up. Function y equals 3x squared plus 2. I'm trying to evaluate exact area from 0 to 1. I'll get the summary. Yeah, here we go. Unsigned area. I'll get a screen grab of that one in the chat. Cool. All right. We got to find our area. What are we going to do? I've also got the procedure written out on the screen share as well, if you'd like to use that for reference. I've seen you come off mute, but nothing's come through just yet. Might be an audio issue. I think that's better now. Yeah.
We find the antiderivative of that.
Yeah, antidiff, that's it. So first things first, trying to find our capital F of x. How do we antidiff this one?
That's x cubed.
Yep, x
That's the
cubed
first term, and the second term, that's 2x.
and 2x. That's exactly right. For those who need it, the table of integrals is up on the screen grab, on the screen share. We're just essentially using the first two dot points there. The 3x squared is handled by the second dot point, and the plus 2 is handled by the first dot point. We can put a plus c in there. It's better to put a plus c in there probably, but you just don't need it when you do the definite integral part. Cool. Next up, separate the interval into positive and negative intervals, if any exist. So we've got to figure out, hang on, over 0 to 1, our domain, do we need to start splitting things off? Do we have both positive and negative area? If so, how are we going to
It's only positive area.
Only positive area,
It's
yep.
a positive graph with a vertical translation up.
That's exactly right, yeah. See our quadratic, it's positive quadratic, shifted up by 2. So any area at all over any domain, it's all going to be above the x-axis. So no splitting is required. We're very happy to now just do integral from 0 to 1 without any anything else. So when you do your notation here, I've seen it before, don't put this one in there. So when you're actually stating what you're doing to find area, make sure you do refer back to the original function. We've already done our antidiff. So
Yeah, I usually write it in the notation before finding the thing.
yeah, sure. Okay, so as in you'll do integral 1 to 0 or 0 to 1 of that f of x underneath it, and then
Yep.
okay, yeah, that makes sense. As long as you don't try to evaluate. Well, yeah, I guess you can look ahead of time before doing any of this as a first step, just to say, hey, where's positive, where's negative. Yeah, that's fine as long as you're doing that first, right? But cool. Okay, so now we just got to evaluate the definite integral of this. What is it going to look like? Capital F of what minus capital F of what?
Of 1 minus f of 0.
That's it. Yeah, top, bottom, in that order. Of course, we have our capital F of x already written there, so it's going to be 1 cubed for 1 plus 2 times 1 plus c, which we can ignore, minus capital F of 0, so 0, 0, and c gets ignored. So, nice and easy. That tells us that the area from 0 to 1, so whatever this would be, has an area of 3. That's pretty much it. All you're doing is getting a rough idea what the graph looks like first, splitting it up if you need to, and then doing your definite integrals. Any questions about that? If not, I'll try to find one that needs a split. Is this cubic gonna get a split? No, but I can make it. Yeah, I'll make it split. Okay, so we're going to do b, but we're going to update it a little bit. Y equals x cubed minus 8 is our function. But rather than do 2 to 4, we're going to do 0 to 4. Okay. Let's have a crack at this one now. So I've already kind of given it away that we do need a split going on. So maybe the first thing we would want to do is get a picture of what our graph might look like. Good news is it's a fairly simple one. Just a cubic with only a translation term. What's it going to end up looking like?
Point of inflection at 0, -8.
That's right, yeah. X cubed, inflection at -8, and it's a positive one, so we're going to have this sort of thing going on. From 0 to 4, really we've only got that part. So finding this now becomes the next natural thing, because if this is 4 or less, then we're happy. If it's more than 4, then suddenly we're going to have to deal with having both a positive and a negative section. Finding an x-intercept, we've done it before. Y equals 0. 0 equals x cubed minus 8. 8 equals x cubed. 2 equals x. That means that's 2. 4 is going to be somewhere over here, which means we're evaluating all of this and all of this. The split is now clear. What's that split going to now look like?
0 to 2 and 2 to 4.
0 to 2 and 2 to 4, absolutely. Now, there's a couple of ways we can handle the 0 to 2 section. We've got to flip that to being positive. What's at least one of the ways we could do it?
Flip the intervals.
Flip the interval, absolutely. So instead of doing 0 on the bottom and 2 on the top, we do a 2 on the top and a 0 on the, 2 on the bottom, 0 on the top. Otherwise, yeah, same function. Y. And we're adding the positive area. If it's already positive, nothing needs to change. 2 to 4 of our function. The other alternative, of course, would have been keep the terminals the same, but put a negative sign on the front instead. Or in other words, negative bracket 0 to 2. that would also do the exact same effect. Cool. All right. So that gives us our intervals that we're trying to find. Good news is the antidiff is clearly going to be the same. It's the same function on both of them. So when we do our capital F of x, we don't need to do it twice. That's our original function. What's the antidiff of this one going to be?
X to the 4 over 4.
4 and
8x minus 8x.
that's it. Minus 8x plus c just to be safe. Yeah, it really is only a safety thing there for bound area related stuff. Yeah, we have our capital F of x. All that's left to do is evaluate each of these. So this is where, when you start splitting the integrals, suddenly you have fairly lengthy working solutions. So for instance, this one, again, it's top take bottom. You got capital F of 0 minus capital F of 2. And you're adding that to capital F of 4, take capital F of 2. You're adding it to this section here, top take bottom of that one. I'll typically put those in brackets, and yes, I know the phone screen is like smaller than what you would write on, but when you start expanding these out, they do get quite lengthy. And again, we kind of saw an example of how lengthy even these can get just by looking at what it looks like on the page on the when we looked at the work solutions of them. If you're in luck, some of the solutions should be like easy enough to evaluate. Like for instance, capital F of 0, that's just 0, so we can just put a nice little 0 there. That's supposed to be an F. I was looking at that symbol, like what the hell did I do there? Minus capital F of 2, so using different brackets where possible can also help as well. Okay, so capital F of 2, we're going to have a quarter 2 to the power of 4 minus 8 times 2. And that's that bit there. Yep. Capital F of 4 is the new one. So that's going to be, let's fix that up again. 1 over 4, 4 to the power of 4. 4 minus capital F of 2. So what you'll notice is when you do this split, you do have duplicate values. So one of the things you can do to save a little bit of time is actually just leave that as capital F of 2. And as long as you don't blend this with that, you can reuse whatever you have here in this spot. That gets pretty risky though, so make sure you're using clear brackets around what's what. Okay, so negative, so 2, 4, 8, 16, divide by 4 gets you back to 4. And 8 to 16 again. Now for this one, 4 to the power of 4 seems like a lot, so I'll do a bit of index manipulation. So 2 squared, so it's actually just 2 to the 8. Then from there, 4 minus 16, so it's going to have minus 12, which we will now copy over to our result for f of 2 over here. 2 to the 8, that's a bit easier to calculate now, so 2, 4, 8, 16, 32, 64, 128, 256. Knowing your powers of 2, very important. Capital F of 2, so we know that's going to be minus 12. Let's put that one in there. Minus 12, so 12. Now a quarter of 256. So divide by 2, 128, 64. So 64 plus 12. Yeah. So 24, 6, 88. So barring any stupid things that I may or may not have done, this is the kind of way I'd start approaching the algebra of these things. you'll find that polynomials get used quite a bit. So being able to break your bases and indexes down into simpler, easier to calculate and count things is good. Using some of the symmetries in the question itself can be also quite helpful to stop you from evaluating things more than a single time. And one of the things I didn't do here was maybe, if you want to be like super safe but a bit longer, is do this one on its own, then somewhere else do this one on its own, and only then add them all up at the end. That'll be probably the thing to start with, so you can just make sure, hey, I can actually do these flat out, at least in some way. And then as you start getting more confident with your arithmetic on them, maybe you can start playing around with a bit more dangerous but faster things. That's about it that we have time for here. So I'll stick around for a little bit if there's anything else to clarify regarding that or otherwise. Any other questions are welcome as well. Otherwise, yeah, I'll see you when I see you next. Thanks, guys.
Thank you.
No worries.
Hey. Okay, I would like to ask, like, okay, if I decide to take engineering,
Mhm.
like, what course did you like take?
So I went to RMIT and I did a bachelor's. Initially, it was a bachelor's in electrical engineering honors, which I then, in the second year, transferred over to electrical engineering, which, by the way, those courses are the same exact first 2 years. So nothing was actually lost in doing that. So if you are interested in those electronics or electrical related stuff, then that's a nice little thing that you can do, and have a bit of flexibility regarding where you go there, because there's a fair bit of overlap in those classes. But yeah, I mean, engineering is pretty broad. There's a whole lot of different disciplines that you can go. That's just the one that I ended up pursuing.
All right. How much of the things you didn't learn officially were actually applied in your job?
So the question is, how much did I learn in RMIT that was applicable for the job?
Yep.
Enough of it. So, kind of like how you're learning methods to have a foundation for uni, you'll learn the stuff in uni to have a strong foundation for when you get into the job. So, one of the things, so my job in the engineering role was firmware engineer. I worked with, we talked about this before, with FPGAs, right?
Yep.
You need at least some exposure to them, otherwise you're going to look a bit stupid, and you may not pass the interview stage if you can't at least demonstrate that you understand what an FPGA is, what the different coding practices are for them, what languages they use. FYI, you've got either Verilog or VHDL for those two things. So as long as you identified at least like one of them to say on the interview you're semi-competent, that's pretty good. But yeah, mainly because in RMIT we learned Verilog. In my job we learned VHDL. They use VHDL for their thing. They're very similar languages, but because of that, having strong foundations in Verilog meant it was quite quick to pick up and just essentially copy syntax related stuff over to the new work environment. So what you're essentially learning even now is less about the concepts and more about how to learn the next thing that you'll need. Definitely the concepts matter a lot. In fact, I literally implemented a bisection method thing in in my job for one of the particular applications that we have. And that's math methods, not even uni. So there's definitely applications for these things that exist out there. A bulk of them will just serve as your foundation that you can then build up on other skills. And you may or may not use some of them literally just out of the box.
Okay.
Is that fair enough?
Yeah. Do you know much about the kernel firmware stuff? Well, no, not firmware. drivers and stuff.
Drivers,
Things
yes.
related
So
to that.
yeah, you're basically talking about effectively the bridge from software to hardware, right?
Yep.
We learned briefly about the whole software stack of what do they call it again? The OSI stack, was it? I forget what the acronym was. Basically, it's like how you go from the basic bit. Oh, it was a network stack, I think. How you go from like the basic bits to the package around it, to so on and so forth, all the way out to the actual software level itself. We learned about it holistically in one of the courses, but being a firmware engineer or doing it at least in RMIT, you would focus around specifically the actual development of the FPGAs themselves, basically.
Okay. Okay.
So, I mean, it kind of sounds like more so if you're doing kernel-related stuff, that's probably closer to software engineering than it is of what I was doing. Only a little bit, though. It's not
Okay.
too far removed.
Okay. One last question. What do you think of the job market now?
Well, so it's obviously going to get more and more technical as you got these things like AI and whatever, right? And that's just been the case historically always, right? The
Yeah.
more sophisticated your knowledge base can be in technology, you just won't get left behind if you're on the bleeding edge, or at least, keeping up to date with where technology is at. Which is why I kind of think of engineering as like it's basically bulletproof, as long as you're a competent engineer that continues to learn about the new things over time. There's always going to be a role for there because businesses and whatever are always going to want to implement technology because it gives them a whole bunch of leverage on what they can do. And so as long as you're doing things where you are building things, making things in a technological way, there should always be a place for you. Now, that being said, a lot of people think that as well. So there's going to be competition, but any good job will have competition. Like, you're not going to find a super cushy job that is also not very competitive. Maybe, but if you do find one that's not that competitive, it's not competitive for a reason, and you probably don't want it. So yeah, overall I think of engineering as quite a safe thing to do in pretty much any of the engineering. And if you're going software, then well, yeah, just based on the things you've been talking about, you're going up and up the ladder of more career viability as far as I'm concerned.
Yeah, okay. Yeah, I guess that's what I wanted to know.
Yeah, you'll always find a job in tech. Like, technology, it's only going one direction. Yeah, so if you are going to pursue this thing, just make sure you stay interested in how things are progressing from year to year, because there is such a thing as becoming an obsolete engineer. Just make sure you don't get like complacent. But it sounds like you're interested in this shit anyway, so I don't imagine that being a problem for you. But yeah, stay interested, stay up to date with where things are headed in your discipline, and as long as you're on the right side of progression, then you'll always have a role somewhere.
Okay.
Make enough sense?
Yeah, I guess that's what I wanted to know.
Yeah, no
Okay,
worries.
so yeah, have a good day.
Yeah, you
See
too.
you.
I appreciate
Good
it.
night.
Good night.